Close your eyes for a second. Now open them. Jupiter is right in front of you. Enormous, ancient, and impossibly beautiful. Bands of cream and amber and rust stretch across its face like brushstrokes on a living canvas. A storm the size of 2 Earths churns silently below. From up here, it almost looks peaceful. Almost. Your speed sensor reads 60 kilometers per hour, then 600, then 6,000. The clouds are rising to meet you faster than your brain can process, and somewhere in the back of your mind, a number clicks into place. Jupiter's gravity is 2.5 times stronger than Earth's. You are not drifting. You are being pulled hard towards the largest planet in the solar system. Your suit's pressure alarm fires. The radio crackles and dies. And this is where the story changes, because Jupiter does not let things go. Before we follow you down, let's understand what you are falling into. Jupiter is not just a big planet, it is a different category of object entirely. You could fit 1,300 Earths inside Jupiter, all of them at the same time, with room left over. Its mass is 2.5 times the combined mass of every other planet, moon, asteroid, and comet in the solar system, put together, all of it. Its great red spot, one single storm system, is wider than 2 Earths placed side by side. That storm has been spinning continuously for at least 350 years. Some scientists think it may have been going for over 1,000. It is a hurricane that has outlasted entire human civilizations. Jupiter has 95 known moons. 4 of them, Io, Europa, Ganymede, and Callisto, are large enough to be planets in their own right. One of them, Io, is the most volcanically active body in the entire solar system. Another, Europa, likely has a liquid water ocean beneath its icy crust, containing more water than all of Earth's oceans combined. Jupiter is not a planet with features. It is a system. And the Sun and Jupiter technically orbit a shared point in space called the barycenter, a point that sits just outside the Sun's surface. Jupiter is so massive it actually nudges the Sun. These two bodies do not work the way textbooks describe. They dance. But the most extreme thing about Jupiter is not what you can see from the outside. It is what happens when you go in. You have entered the upper atmosphere. The first thing you notice is the smell. Except you cannot actually smell it. Because if you opened your visor up here, you would be breathing ammonia and hydrogen sulfide. The scientific description is a mixture of toxic gases. The honest description is the worst smell in the universe, concentrated and then pressurized. The clouds that looked so soft and dreamy from space are up close walls of ammonia ice crystals, moving sideways at 500 kilometers per hour. You are not flying through clouds. You are being thrown through them, tumbling at speeds that would reduce most aircraft to scrap metal in seconds. Then the lightning starts. Jupiter's lightning bolts are not like Earth's. Each one carries roughly 1,000 times more energy than a typical terrestrial strike. A bolt detonates 40 kilometers to your left. You feel the electromagnetic pulse rattle through your suit like a physical blow. Your visor display scrambles. Your altitude sensor resets. For 3 seconds, you have no idea how fast you are falling. Temperature in the upper cloud deck, negative 145 degrees Celsius. Cold enough to turn your fuel lines brittle. Cold enough to freeze the lubricant in every mechanical joint on your suit. Your suit holds. The engineering team that designed it was brilliant. But the clouds were never the real danger. The real danger is what is below them, 100 kilometers down. The pressure is already 10 times what you would feel at the bottom of Earth's deepest ocean trench, the Mariana Trench, which took humanity decades of engineering to reach. You have passed that threshold in minutes. Your suit compresses around you. The reinforced panels groan. This was expected. The engineers planned for this. They planned for 200 kilometers too, and 300. But here is the problem. You are still accelerating. Jupiter's gravity does not forgive deceleration. Every second you are moving faster, and every second the atmosphere around you is getting thicker, hotter, and heavier. By 500 kilometers down, The temperature has climbed to over 1,000 degrees Celsius. That is hotter than flowing lava on Earth. The gas around you is no longer cold cloud. It is a crushing, invisible furnace, pressing in from every direction simultaneously. But here is the thing that most people miss when they imagine falling into Jupiter. There is no floor. On Earth, if you fall into water, you eventually touch the bottom. Jupiter has no bottom, no solid ground, no bedrock, no surface waiting to catch you. You will fall and fall and fall until the pressure and heat take you apart atom by atom, long before you reach anything resembling a center. 20,000 kilometers down, something changes. The pressure here is so extreme that hydrogen, the gas you have been falling through for hours, can no longer remain a gas. The individual molecules are being squeezed so close together they begin to behave like a liquid. Not water, not anything familiar. Liquid hydrogen, dense and dark and electrically silent, stretching in every direction without a visible surface or floor. You are no longer falling through atmosphere. You are sinking into an ocean that has no shore. But that is not the worst part, because something stranger, something that bends the rules of chemistry itself, is waiting below. Here is something remarkable about Jupiter that most people never learn in school. At roughly 40,000 kilometers below the cloud tops, the pressure reaches 3 million times Earth's atmospheric pressure. At this depth, hydrogen does something that, under any normal circumstances, it simply does not do. It becomes metallic. What does that mean? Think of a normal hydrogen atom, one proton, one electron, the simplest element in the universe. In normal conditions, that electron is tightly bound to its proton. They move together, locked. But under pressures this extreme, the electrons are literally squeezed free. They stop belonging to any individual atom. They become a shared sea of charge, flowing freely through the material, exactly the way electrons flow through copper wire or iron or any metal you have ever touched. The hydrogen has not turned into metal. It has become metallic. It conducts electricity the way metal does, while remaining chemically pure hydrogen. Nothing in a laboratory on Earth can reproduce this. We have only ever produced tiny amounts of metallic hydrogen for fractions of a second under experimental conditions. Jupiter has an ocean of it, tens of thousands of kilometers deep, that has existed for 4 billion years. And because this metallic hydrogen is spinning with Jupiter's rapid rotation, Jupiter completes one full rotation in just under 10 hours. The fastest of any planet in the solar system, it generates a magnetic field. Not a modest one. Jupiter's magnetosphere is the largest structure in the solar system outside the Sun itself. It extends nearly 5 million kilometers toward the Sun and stretches almost 1 billion kilometers in the opposite direction, past the orbit of Saturn. If we could see it with our eyes, it would appear 6 times wider than the full moon in our night sky. At the very center, scientists believe there is a core, possibly solid, possibly dissolved by pressures and temperatures that no material in the universe could survive intact. It may contain rock, ice, and heavy metals compressed to densities we cannot measure directly. It remains, to this day, one of the most debated objects in planetary science. Jupiter is a gas that became a liquid, then a metal, then something we have no good word for, all inside the same planet, just depending on how deep you go. Here is a fact that should stop you cold. We have already done this, not with a person, but with a machine. And it heard things we never expected. Before 1995, Jupiter's interior was almost entirely theoretical. We had observed it from the outside, photographed its clouds, measured its gravity from a distance, but no one had ever sent anything directly inside. Scientists had models, they had mathematics, they had educated guesses. What they did not have was data. NASA built a probe, a small, rugged, armored spacecraft, and attached it to the Galileo mission. On December 7, 1995, they aimed it at Jupiter and let go. The probe hit Jupiter's atmosphere at 47 kilometers per second. That is approximately 170,000 kilometers per hour. In the first 120 seconds, friction from the atmosphere heated the probe's shield to 16,000 degrees Celsius, hotter than the surface of the Sun. A significant fraction of the shield material burned away entirely. This was planned. The engineers built the probe to ablate, to sacrifice its own outer layers to absorb the heat, the way a meteor burns up to protect whatever is inside. A parachute deployed. The probe slowed, and then it began to transmit. For 58 minutes, the Galileo probe descended through Jupiter's atmosphere, sending back real measurements: temperature, pressure, wind speed, lightning frequency, chemical composition. Scientists on Earth listened in real time. Some of them had worked on this mission for over a decade. For 58 minutes, they heard Jupiter speak. Then the pressure became too much. The probe went silent. It continued falling, deeper and deeper, until it was dissolved, its atoms absorbed into the planet. What the data showed surprised almost everyone. The upper atmosphere had far less water than models predicted. The winds deep in the atmosphere were faster than the winds near the surface, the opposite of what scientists expected. The helium abundance was different from theoretical calculations. Jupiter, on the inside, was stranger than the outside suggested. Today, the Juno spacecraft orbits Jupiter on a highly elliptical path, diving close to the cloud tops before swinging back out to safety. Its instruments measure Jupiter's gravity field, magnetic field, and deep atmospheric composition with unprecedented precision. Each orbit peels back another layer of the mystery, but even Juno cannot go inside. It can only listen from above, like pressing your ear against a wall and trying to understand the conversation happening in the next room. We sent a machine to die inside Jupiter just to hear what it had to say, and what it said changed everything we thought we knew. Now step back. Pull your perspective out from that falling probe, out from the metallic hydrogen ocean, out through the clouds and the lightning and the ammonia ice. Rise up until Jupiter is just a bright dot in the black. From here, you can see the whole solar system. And from here, something becomes clear that you cannot see up close. Jupiter is not just a planet in the solar system. It is one of the reasons the solar system works the way it does. Jupiter's gravity is so dominant that for billions of years, it has acted as a gravitational shield for the inner planets. Comets and asteroids on collision courses with Earth, Venus, and Mars have been captured, deflected, or simply absorbed by Jupiter before they could complete the journey inward. The rocky planets exist in a relatively calm neighborhood, partly because Jupiter has been running interference from the outside. In July 1994, the world watched a comet called Shoemaker-Levy 9 break apart and crash into Jupiter in 21 separate impacts over 6 days. The largest single impact released energy estimated at 600 times the total nuclear arsenal of all nations on Earth. It left a dark scar in Jupiter's atmosphere larger than our entire planet. Had that comet arrived a little differently, on a trajectory toward Earth rather than Jupiter, this video would not exist, neither would anyone to watch it. Jupiter also sculpted the asteroid belt. Its gravitational influence during the early solar system repeatedly disrupted the asteroid belt region, preventing the rocks there from ever accumulating into a full-sized planet. Without Jupiter, there might be an additional rocky planet orbiting between Mars and Jupiter today, and the orbital dynamics of the entire inner solar system would be fundamentally different. And its magnetosphere, that vast invisible structure generated by the metallic hydrogen ocean deep inside, reaches out to engulf Jupiter's inner moons. Europa, with its hypothetical underground ocean, sits inside Jupiter's magnetic field. That field deflects harmful radiation, potentially playing a role in maintaining the conditions that might make Europa habitable. Jupiter may be protecting the very place in the solar system most likely to harbor life beyond Earth. Jupiter did not just form alongside our solar system, it helped build ours, and it is still protecting us from the outside. Jupiter is made mostly of hydrogen and helium. These are the same two elements that make up the Sun. They are the most abundant elements in the universe, And had Jupiter accumulated roughly 80 times more mass during its formation, the nuclear fusion reactions in its core would have ignited. Jupiter would have become a star. Our solar system would have been a binary star system, two suns. Earth, as it exists today, would almost certainly not have formed. The orbital zone that produced our planet would have been too gravitationally chaotic, too thermally extreme, too unstable for a rocky world to coalesce and survive. We exist, in part, because Jupiter failed to become what it almost was. Astronomers have now found Jupiter-sized planets in hundreds of other solar systems. Many of them are hot Jupiters, gas giants that formed far from their stars and then migrated inward, dragging through the inner planetary zone like a wrecking ball, scattering or destroying any rocky planets in their path. Our Jupiter stayed put. It formed in the outer solar system and, despite some early migration, settled into its current orbit and held there. That was not inevitable. That was, by the standards of planetary science, unusual. And on deeper timescales, this arrangement is not permanent. Jupiter's gravitational interactions with the other planets cause slow, subtle changes to everyone's orbital parameters over tens of millions of years. There are scenarios, low probability but mathematically real, in which Jupiter's influence could eventually destabilize Mercury's orbit, setting off a chain reaction that reshapes the inner solar system entirely. The clockwork is precise for now. It has been for 4 billion years. But the universe does not offer permanence. It only offers moments of stability between changes. We are living in one of those moments right now. A window of orbital calm held open by the gravity of a planet that almost became a star.
We are alive today, at least in part, because a planet that could have burned, didn't. Come back now. Back to the fall. The clouds are gone above you. The lightning has faded into silence. There is no up and no down, no light, no surface, nothing to orient yourself by. You are suspended inside an ocean of liquid hydrogen that extends in every direction without end. The temperature is high enough to melt iron. The pressure is high enough to crush a submarine to the size of a fist. You are, by any useful definition, gone. But here is the thing about Jupiter: it does not destroy what enters it. It transforms things. Your atoms are still here. The carbon in your body, the oxygen in your air tanks, the iron in your suit's frame, none of that ceases to exist. It disperses. It mixes. It becomes part of the largest collection of matter in the inner solar system. You become, in a very literal sense, part of Jupiter. The Galileo probe is still in there too. Somewhere in the metallic hydrogen, millions of kilometers below the cloud tops, the titanium and aluminium and copper that engineers assembled in a clean room in California in the 1980s are dissolved into a planet that has existed for 4 billion years. A machine that human beings built with their hands, that carried instruments calibrated with human precision, that transmitted data through human mathematics back to human ears, is now Jupiter. It will remain Jupiter for longer than the human species has existed. Longer, perhaps, than the human species ever will exist. And one day, in roughly 5 billion years, when the Sun expands into a red giant and its outer layers engulf the inner solar system, Jupiter itself will be consumed. Its hydrogen and helium will feed the dying star. The metallic ocean, the storms, the 400-year hurricane, all of it will be absorbed. Jupiter will become the Sun. And the Sun will drift away as a cooling white dwarf, carrying everything inside it into the long, cold quiet of the universe's old age. Nothing is permanent. Not the probe. Not Jupiter. Not the Sun. Not us. But nothing disappears either. It just keeps falling, deeper and deeper, into the next thing. Jupiter swallowed a spacecraft built by human hands. And somewhere in the dark, it is still keeping it. The universe does not destroy the things we send into it. It just holds on to them, long after we have stopped looking. If falling into Jupiter left you with more questions than answers, subscribe. Every week we drop you into a new corner of the universe. And if you want to see what Europa's hidden ocean might be hiding beneath all that ice, the next video is already waiting for you.